Good morning, class. I feel that we should commence now. So, as we have it today on the timetable, we have physics spec. The physics spec is just a short form of writing special topic instead of us looking into the past question. So, we are going to pick one of the special topics that we have in physics that probably we might not get into it um, in one way or the other. So that's the essence of what we are going to be doing today. So I'm going to share my screen now, and the class is going to commence the way it's supposed to. So can you see the screen now? Can you guys see my screen?
Yes, sir.
Okay. So the topic we want to look into this afternoon is basic electronics. Basic electronics. I think so this is too small. Now, when we talk about basic electronics, we want to talk about the aspect of solid or the characteristics of solid. When we talk about solid, we all know what solid simply means. A material whose intermolecular force is very, very strong. That is, a material that the force of attraction between its molecules, they are very strong. A material that we can refer to as a rigid body. When I say material is a rigid body, what it simply means is that when you shake the material, the molecules that made up that material, they will leave their main position. Such materials are called rigid body. So example is solid. But when it comes to electronics, or electricity, we talk about solid in three ways. We can categorize solid into what? Three. We have what we call conductor. We have what we call insulator. We have what we call semiconductors. So these are the three things that we refer to as solid. So when you say solid, you talk about what? Conductor, insulator, and semiconductor. As far as electricity or electronics is concerned. Now, how do we know conductor? How do we know insulator? How do we know semiconductors? Now, for every solid, there is what we call band theory of semiconductors or atomic theory. Are you getting this now? You guys, is it that anybody can hear me clearly? Is there anyone who can't hear me clearly? Hello, is there anyone that, okay, let me ask, is there anyone that is hearing me clearly? Can somebody unmute his or her mic and respond to my question? Is anybody hearing me clearly?
Yes, sir.
So if you are not hearing me clearly, is that you increase your own volume or you check your network? Because I think I'm audible enough.
Yes, you can.
All right, thank you. Now we're talking about basic electronics. And I want you to pay maximum attention to this topic with the way I want to teach it, such that you can have everything upstairs without cramming it. When you say solid, we can categorize them into three: conductor, insulator, and semiconductor. So for every material that we refer to as solid, we have what we call three bands. The bands are conduction band. When we talk about the bands, they are conduction band, conduction band, conduction band. We have a forbidden band. You can either call it forbidden band or you call it fabricated band. Forbidden band, or you can call it fabricated band. Then we have valency band. Now these are the three bands that we have in every material. Are you getting it now? When you have a solid material, that material has a conduction band, it has forbidden or fabricated what? Band, and it has a valency band. Now if it is a conductor, if the material is a conductor, then we are going to have that. Okay, let me redraw this diagram here. Okay. Alright, so if I have this, for if the material happens to be a conductor, for a conductor, I have this, and I have this. Now, what's the meaning of this? This is what? The valency band, and this is the conduction band. So, electrons are full, that you have what? A full electron in the valency band for a conductor. Then the conduction band is partly filled with electrons. Are we together now? For conductor, the valency band is filled with electron, while the conduction band is partly filled with electron. Then the forbidden band, it has no forbidden band, or let's say the forbidden band is shrink. That is, it has a very tiny forbidden band. Now, because you have electron in the conduction band, that is the reason why this material is going to conduct electricity. Are we together now? So you have what? The electron in the forbidden band to greater than the electron in the conduction band. But if the material happens to be an insulator, if it is an insulator, we are going to add that it has a conduction band, it has a valency band, and it has a very wide forbidden band. So in the valency band, there is an electron there. You have a partly filled of electron. But in the conduction band, there is no electron, and it has a very wide gap forbidden band. So when there is no electron in the conduction band, such material will not be able to conduct electricity. And that's the reason why an insulator cannot conduct electricity, because there is no electron in its conduction band. Okay, if it is now semiconductor, for example, if we have semiconductor like this, for semiconductor, they have a tiny forbidden band, and instead of in their valency band, instead of them to have electron, they have what we call holes in their valency band. They have holes in their valency band, and in their conduction bands, they have what? Electrons. And the number of electrons in the conduction band for a semiconductor is the same as the number of holes that you have in the valency band. So that is, electron in the conduction band is equal to the holes in the valency band. So any material that has holes in the valency band and electron in the conduction band and it's equal, such material is referred to as semiconductor. And any material that has a very wide forbidden band and no electron in the conduction band is referred to as insulator. And any material that has more electron in its valency band than it does in its conduction band and it has a very shrink forbidden band, such material is called a conductor. So I want to believe now that everybody understands how we categorize material in physics, especially electronics. We have conductor, we have insulator, we have semiconductor. Now, in some of our topics under electricity, we have discussed conductor, we have discussed insulator, especially when we are talking about Ohm's law. But under electronics, like when you check your gadgets, you open your laptop, you have piles, you have transistors, you have capacitors, you have what? Diodes. All of those components of your electronics, they are semiconductor. So in this topic, we are going to be looking at semiconductor in details. So we start by looking at the definition of semiconductor. Now when you say semiconductor, what is semiconductor? Semiconductor. Semiconductors are materials. Semiconductors are materials whose conductivity. Semiconductors are materials whose conductivity is intermediate between conductor and insulator. I'll take it again. Semiconductors are materials whose conductivity is intermediate between conductor and insulator. What do you mean by their conductivity is intermediate between conductor and insulator? Is that when you say a semiconductor, they are materials that have the ability to conduct electricity and they might not also conduct electricity. Are you getting where I'm coming from now? They can conduct and they might not conduct. So when you have semiconductor in their pure state, semiconductors in their pure state, you call them their group 4 elements. Group 4 elements. And when you talk about group 4 elements, we have example of group 4 elements to be silicon and germanium. So these are very common material, very common semiconductor material. But normally, group 4 elements, they are semiconductors. So if you pick any group 4 elements, they are semiconductor. But because of their period, I'm getting this now, because of their period, germanium and silicon, they are widely used compared to any other group 4 element as a pure semiconductor. Now, we all know that the group 4 elements, they exhibit what? They exhibit covalent bonding. Are we together now? Covalent bonding between their atoms. So that means they do not contain ions necessary for electrical conduction. So if they do not contain ions that is necessary for electrical conduction, then we say semiconductor in their pure state, they are insulator. Are we together now? Semiconductor in their pure state, they are insulator. And we call them intrinsic semiconductor. So when I say intrinsic semiconductor, we are talking about semiconductor in their pure states. All these, they are what? Group 4 elements, and they consist of what the exhibitor we refer to as covalent bonding. You need to note that semiconductor exhibits covalent bonding, and they do not contain ions that can enable them for electrical conductivity. For that reason, semiconductor in their pure state, that is intrinsic semiconductor, they are insulator. But when you say they are insulator, what type of insulator? Is it an insulator that cannot conduct electricity at all? No. It is an insulator that can conduct electricity by increasing the amount of heat energy. When you increase the amount of heat energy on intrinsic semiconductor, it results to low resistance. That is, when you talk about the relationship between temperature and resistance for a semiconductor, the higher the temperature, the lower the resistance. So temperature is inversely proportional to resistance for a pure semiconductor. The higher the temperature, the lower the resistance. Are we together now? So they are poor conductor in their pure state. So they require a very high amount of temperature to reduce their resistance. Unlike a pure metal, for a pure metal, the higher the temperature, the higher the resistance. But for semiconductor, the higher the temperature, the lower the resistance. Is that okay now? Alright, so if that should be the case, we have that the charge carriers are holes and electron. Holes and electron. Remember, when you have an electrolyte is a conductor whose charge carriers are ions. When you have a conductor is what? The charge carrier for conductor is electron. When you have conductor that is like pure metal, the charge carriers are electrons. When you have electrolytes, the charge carriers are ions. When you have semiconductor, the charge carriers are holes and the electron. Do you understand that now? So holes is the positive charge carrier. Holes is the positive charge carrier in a semiconductor, and electron is the negative charge carriers. Do you understand that now in a semiconductor? So I'll quickly recall that before we move on. We said that semiconductors are materials whose conductivity is intermediate between conductor and insulator, and we said in their pure state, that is in their pure state, that is intrinsic semiconductor, we said they are group 4 elements, and they exhibit what? Covalent bonding. That means they don't have sufficient ions to carry forward electric charge. Therefore, they are poor conductor or an insulator. When you increase the temperature of an intrinsic semiconductor, the resistance reduces. And this is something that examiner always asks. Examiner can ask you that what is the relationship between conductor and semiconductor? When we talk about the relationship between conductor and semiconductor, is that for conductor, the higher the temperature, the higher the resistance. For semiconductor, the higher the temperature, the lower the resistance. Do you understand that now? And the charge carriers for semiconductors are holes and electrons. Holes, they are the positive charge carrier, and electrons, they are the negative charge carrier. I hope you understand that now. Okay? If you really want a semiconductor, to conduct better, remember, I want you to note something so that when you get to exam, you are not going to be confused. And I think, if I can remember vividly, there is this particular question. I can't really tell the year in which the question was asked. The question says that intrinsic semiconductor Remember, when I say intrinsic semiconductor, they are saying semiconductors in their pure state. So the question now states that intrinsic semiconductors, A, do not conduct electricity at all. B, are used as conductors in electronics rather. C, conducts better at higher temperature. D, have no resistivity at lower temperatures. E, have high resistivity at higher temperature. When this question is put to you, don't just think that semiconductor in their pure state, they cannot just conduct electricity. No. You should understand that while they are in their pure states, they might be acting as an insulator, that is a poor conductor. But if they see a very high sufficient amount of heat, they are going to conduct electricity. For that reason, the correct answer to this question is going to be that they conduct better at higher temperature. But should in case there is no higher temperature and you want your semiconductor to conduct very well, then what you need to do is to add impurity to the pure semiconductor. Are we together now? So when you add an impurity to an intrinsic semiconductor, it allows the rate of conductivity to increase. Are we together, class?
Also, the possibility to
Okay, so when you add an impurity, when you add an impurity, when you add an impurity to a pure semiconductor, when you add an impurity to a pure semiconductor, plus heat, they conduct better. Are we together now? When you add an impurity to a semiconductor, they do what? They conduct better. But immediately you add an impurity to a semiconductor, that semiconductor, instead of being an intrinsic semiconductor, it becomes extrinsic semiconductor. Are we together now? So semiconductor in their impure states, they are what we call extrinsic semiconductor. That is semiconductor with an impurity. Now this semiconductor, they can conduct electricity better compared to the pure semiconductor, and they are divided into two. We have what? We have the p-type semiconductor, that is the extrinsic semiconductor, are divided into two, the p-type and the n-type. Are we together now? So how do you get the p-type and how do you get the n-type when you talk about extrinsic? Now we have what we call dopants. We have what we call what? Dopant. When it comes to you adding impurity to a pure semiconductor. Let's say this is an intrinsic semiconductor. The process of adding an impurity, the process of adding an impurity, the process of adding an impurity to a pure semiconductor, is called doping. So when you dope a semiconductor, what it means is that you add an impurity to the semiconductor. So doping is the process of adding an impurity to a pure semiconductor. So when we now talk about this impurity can either be trivalent atom or pentavalent atom. So when we say trivalent atom, we are talking about what? The group 3 element. When we say pentavalent atom, we are talking about the group 5 element. Are we together now? So when you add trivalent atom, that is group 3 element. So who can give us an example of group 3 element here?
Aluminium.
Aluminium. So when you say trivalent atom, we have aluminium. Which other one? We have indium. Which other one?
Boron.
Boron. Thank you. Which other one? I think 4 is okay. So let me say thallium. So these are trivalent atom. So we have that when you have intrinsic semiconductor plus either boron, aluminium, indium, thallium, that is a trivalent atom. When you have intrinsic semiconductor and a trivalent atom, you have what we call what? P-type semiconductor. The P-type semiconductor is what you are going to have if you add what? Trivalent atom to an intrinsic. But when you have a pentavalent atom to an intrinsic semiconductor, you have what? N-type semiconductor. And pentavalent atom, we said they are group 5 elements. So what are the examples of group 5 elements? Pentavalent. So example of group 5 elements?
Nitrogen.
Nitrogen, phosphorus,
Oxygen.
okay. Which other one?
Nitrogen.
Phosphorus, nitrogen, right?
Yes.
Okay. Which other one? Arsenic. Any other one? Okay. Antimony is there. Okay, I think that one is fine. So there are more elements under what? Pentavalent. So for the pentavalent, if you have phosphorus to any group 4 element, or you have what? Nitrogen or arsenic or antimony, you are going to have the N-type semiconductor. So for intrinsic semiconductor that you add trivalent atom to, you are going to have the P-type semiconductor. So for P-type semiconductor, the major charge carrier for P-type semiconductor, they are holes. And the major charge carrier for N-type semiconductors, they are electrons. So that means for the P-type, they have more holes compared to electrons. For the N-type, they have more electrons compared to holes. Am I making sense now?
Yes, sir.
Okay, so I want to believe everybody understand this. So let me quickly recall this aspect again before I move to the next one. We said semiconductors, when you add impurity to them, they conduct better compared to when they are in their pure state. And any conductor that you have, any semiconductor with an impurity, they are referred to as extrinsic semiconductor. That is, extrinsic semiconductor, they are semiconductors in their impure states. And we said the process of adding an impurity to a pure semiconductor is called doping. And what we call dopants, that is the atom that we use to dope a pure semiconductor, they are two, remember, trivalent atom and pentavalent atom. Trivalent atom, they are the group 3 elements, and pentavalent atom, they are the group 5 elements. So trivalent atom include aluminium, indium, boron, thallium. And we have pentavalent atom to include phosphorus, arsenic, and antimony. When you have what? The trivalent atom to an intrinsic semiconductor, you have the p-type semiconductor. When you have what? Pentavalent atom to an intrinsic semiconductor, you have the n-type semiconductor. Then for the p-type semiconductor, the major charge carrier there, they are holes. And for the n-type semiconductor, the major charge carriers there, they are electrons. I hope you understand this now. So the next thing we want to look at now is how it affects what? The resistance of a semiconductor. That is, if I plot the graph of resistance against temperature, what is it going to look like? Because I discovered that as a student of physics, we need to get conversant with laboratory experiment. But it's so surprising, the school curriculum, or let me say the school timetable, did not really give room for us to have enough practical section. And some schools do not have apparatus, and school that has apparatus to even cover the skin and not have enough practical is not just too visible. So with that, we are not really conversant with how graph should look like. An examiner will not care about that. They will always give us questions that has to do with graph. So when you talk about semiconductor and you plot resistance against temperature, how will the graph look like? When you talk about conductor and you plot resistance against temperature, how will the graph look like? So let's consider that now. Okay, so we have heat and semiconductor. Heat and semiconductor. So when we talk about heat and semiconductor, we have that semiconductors are classes of solid with conductivity. That is, their ability to conduct. When you talk about the conductivity of a material, every material has their own conductivity. The higher the conductivity, the better conductor the material is. And the lower the conductivity, the poorer it is to conduct electricity. So for semiconductor, their conductivity ranges between 10 raised to power minus 5 and 10 raised to power 3 watt per seconds per centimeter. Watt per seconds per centimeter. So do you get this now? That's for what? That's for their conductivity. And their resistivity, it is between 10 raised to power minus 6 and 10 raised to power 12 watts per centimeter. Are you seeing this now? So if you look at this now, I want you to observe something. Why am I giving you this? Why do you need to have idea of this figure? Is because when you talk about a semiconductor, they are just purely group 4. But when you talk about conductor, there are different type of conductors. And conductors are, because they are different, for example, silver, copper, aluminium, they are all conductors. They have different conductivity. So examiners don't usually use their conductivity value to test you because they are of different value. But you see semiconductor, examiner are going to test you by using the conductivity of semiconductor to test you if you can identify a semiconductor using their conductivity value. Am I making sense now? Using their conductivity value, can you identify that this material is a conductor? That is why I'm giving you the conductivity value. Within 10 raised to power minus 5 to 10 raised to power 3 is very small compared to their resistivity value. Their resistivity value means their ability to resist ranges from 10 raised to power minus 6 down to 10 raised to power 12. That's kind of huge. I'm getting it now. So you need to You need to have that in mind for subsequent response to question. So when you plot the graph of Let's say we are given resistance and we plot the graph of resistance against temperature. What are we likely to have? So this is resistance on the vertical axis and this is temperature on the horizontal axis. If it is a semiconductor, you are going to have the graph to look like this. And if it is what? If it is for conductor, you are going to have a straight line graph like this. Am I making sense now? So this is for conductor. Okay, sorry. Conductor. And this is for semiconductor. So if it is what is it called? Insulator. For insulator, you have it like this. So if it is insulator, you just have it to be the same. The resistance is constant irrespective of the temperature. If you like increase the temperature, if you like decrease the temperature, for insulator it remains the same. But for semiconductor, as you are increasing the temperature, the resistance is reducing. You can see here, when the temperature here is, the amount of temperature here is smaller. Let's say this is 1, this is 2, this is 3, this is 4. You can see that as the temperature is increasing, you see that the resistance is doing what? Is just decreasing. But when you look at that of conductor, as the temperature is increasing, you can see that the resistance is also doing what? Increasing. So we said resistance is proportional to temperature for conductor, and resistance is inversely proportional to temperature for semiconductor, and resistance is constant for insulator. Does anybody understand this better? Do you understand this, guys?
Yes, sir.
Okay, so a quick recap under this heading before we move to the next one is that whenever you apply it to a semiconductor, it increases what? The rate at which it's going to conduct, because the resistance is set to reduce. And the conductivity for a semiconductor, it ranges between 10 raised to power minus 5 to 10 raised to power 3, while their resistivity ranges between 10 raised to power minus 6 and 10 raised to power 12. For conductor, the resistance is proportional to the temperature. That is, the higher the resistance, the higher the temperature, and vice versa. But for insulator, it is constant. So that's that about that. So let's move on to another aspect of the topic, and that is the concept of semiconductor devices. Semiconductor devices. So when we talk about the devices of semiconductor, the very common one that we have is the diode. Everybody know diode. Or is everybody here? The very common diode that everybody know is the LED. LED simply means light emitter diode. Light emitter diode. So it's a very common one that virtually everybody uses it. Aboki uses it, you use it, because it's what they used to make all these touchlights that we buy from them. Alright, so this one is very, very common. But we have other diodes other than this. There are other diodes that they are typically used in electronic components other than bringing about light. Are we together now? So for example, we have what we call junction diode. Junction diode. I usually call this thing Diodes. If you don't, if you might not, if you know that the what's it called, the spelling will give you error. You can just spell it in Yoruba way, D or D. That's what we call diode. Alright, so back to class. Junction diode. When we talk about the junction diode, how do we get it? We get junction diode by picking an intrinsic semiconductor. Let's say this is an intrinsic semiconductor. We pick an intrinsic semiconductor like this. So if you pick this intrinsic semiconductor, this is intrinsic. Now, let me say this is side A and this is side B. If you take this side A and you dope it with trivalent atom, that is, you part trivalent atom, which are an impurity, you add this to this part, with this part, and you pick pentavalent atom and add this to this side. It will make this semiconductor to become a junction diode, whereby we are going to add it to be PN. Are you seeing this now? PN. And then we have it here, a straight line here. So let me just put it here, a straight line here. Are you seeing this now? So this is P, where we are going to have more O's. And this is what? N, where we are going to have what? Electron. So you are having N here simply because you pour what? You pour the so-called pentavalent atom, you add this to this side, and you add what? Trivalent atom to this side. So we have what? PN. Are we together now? So by doping one end of an intrinsic semiconductor with trivalent atom and doping the other end with pentavalent atom, we are going to have what we call junction diode. Are we together now? So it's a junction diode because it is a junction with alternating charges due to diffusion or attraction of opposite charges to form electron holes pair. I'm getting it now. So that is what I'm saying here is that when you finish doing this, you have the holes in this place interacting with electrons here. And the electrons in this place will also be interacting with the holes here. Then you can have something like this. So you can therefore have something like this. You can have this. So this will give us so here now we are going to have electrons moving down to this side, then we have holes moving down to this side. Are we together now? Because of that interaction between them. Now the transition region between P and N is what we call PN junction. So when you can see the transition between this, so this is called PN junction now. PN junction. Are we together now? So this center, that is this center, is called depletion layer. That is the barrier between this side and this side, between the P and the N. That's what we call depletion layer, or we call it resistance layer. We call it resistance layer, or we call it depletion layer. So the junction, the thickness of this junction is just is within 10 raised to power minus 4 in centimeter to 10 raised to power minus 6. Sorry, what am I saying? The thickness of this, rather. The thickness of this junction here is either 10 raised to power minus 4 centimeter or 10 raised to power minus 6 meter. So that's that. So the junction is also called depletion layer, like I said, or you call it resistance layer, because it prevents a further flow of charges. So because of this particular boundary here, there is no flow of charges. Are you together now? So we have that as a PN junction. So now what is the symbol for diode for this particular junction? So we have this. Okay, I think the AI is supposed to help me draw this better. Okay, so I have that. I have this, and this. So when you look at this now, this is called junction diode. Junction diode. Are we together now? So this is the N type, and this is the P side. So the P side is always the base. Are we together now? And it's always pointed towards what? The N side. So this is the negative, and this is what? The positive. Now we have another type of diode. that we call zero diode. Okay, so we have this. So when you see this particular symbol, this one represents a Zener diode. So this is Zener diode, this is what? Junction diode. Now, we have what we call bias. And when you talk about bias, we are talking about the connection of a semiconductor. You can conduct a semiconductor in three different ways. The first way is when you connect it like this. Let me just use this diagram. If I have this, so let me say I have something like this. So this is P and this is N. So if I connect this P type like this, I have this like this. You see, there's no battery here. So when there is no battery, we call it no biasing. When there is no battery. But when there is battery and you connect the P type, when there is battery and you connect the P type to the positive side of the battery, just like this. When you connect the P type to the positive pole of the battery, we call this forward bias. Forward bias. And when you connect, when you have this, so if I have this is P and this is N. So if I have this connected this way, so this is the negative side of the battery and this is the positive pole of the battery. So when you connect the N type to the positive pole of the battery and the P type to the negative pole of the battery, we call this one reverse bias. Are we together now? So you have forward bias and then reverse bias. Now when you say forward bias, or let me start from no bias. No bias means when the battery is connected, the net flow of charge in any one direction is zero or equal and opposite flow of charges are produced even as the magnitude of the carriers may not be equal. So when you say no bias, no bias simply means there is no current flowing inside the circuit. I'm getting where I'm coming from now because there is no source of voltage in it. But when you say forward bias simply means that, because one thing is this, normally we have two types of current. Let me break it down like that. We have two types of what? Current. We have what we call conventional current, and we have what? We have non-conventional current. When you talk about conventional current, you are talking about current that flows from the high voltage source down to low voltage source, instead of current that flows from the low voltage source to the high voltage source. Now, in semiconductor, because of the behavior of transistor, when we get under transistor, I'll be explaining more about what I'm trying to say here. Because of the behavior of transistor, we use what? Conventional current under semiconductor. That is, we consider currents to be flowing from positive to negative. So when you connect positive pole of a junction diode, when you connect it to what? A positive pole of the battery, current is going to flow well, we are going to have low resistance, and then the load is going to on light. I'm getting it now. For that reason, forward bias has what? A low resistance. I want to get now current flow from positive to negative, and the load on it will what? Will on for forward bias. But for reverse bias, we are going to have current to flow from negative to positive. I want to go now. Then we are going to have high resistance, and the load on it is not going to on. So those are the differences between forward bias and reverse bias, and then no biasing. Is that okay now? Now, whenever you want to plot a graph for junction diode, if I plot a graph of current against voltage for a junction diode, if I plot a graph of current against voltage, let's say I have something like this. If I have something like this, so when you see this kind of a graph, when you plot current against voltage, this is what? This is called PL junction diode. Are you together? So here is going to be reverse bias. Sorry, what am I saying? Here is going to be forward, and here is going to be what? Reverse. You can also have the graph to look like this for other type of diode. You have it like this. So this is going to be forward, voltage against current. So this is going to be forward, and this is going to be what? Reverse. And if I have something like this, if I have this and this is going to be for zero diode. So current against voltage. So for Zener diode, you have this. This is Zener diode. Okay, so this is forward, and this is reverse. I hope you understand this now. So the maximum reverse bias potential that can be applied before entering the Zener region is called the peak inverse voltage. So that is at this point here. This point here is called the peak inverse voltage. Is that okay now? Or peak reverse voltage, anyone? So you can take it down now, and let's look at the uses of semiconductor diodes. What are the uses? That is the usage of semiconductor diodes. Okay. Number one, when we talk about junction diode, it is used as a rectifier. It is used as a rectifier. So that is when you want to convert AC to DC, rectifier, or you call it current rectification. From AC to DC. So you always have it in your charger. There's no way you are not going to have it, because your charger, the current coming from your socket, it is an AC current, a pulsating current, and when it's about to enter your phone, there is need to convert it to DC. That's why some of you can still take the risk of plugging your charger and be using your tongue to test if there is current in it. Am I making sense now? So you are able to do that just because the diode inside the charger has convert the AC current to DC. DC current is what entering your what enters into your phone. Are you getting it now? So, but the danger in you using your tongue to test if your charger has current or not is if the diode inside the what inside the charger, if it fail, then it's just Allah Akbar 4 times. Believe me, we understand that. Am I making sense now? So, because although it's not going to be the perfect rectification, I want you to note that. I want you to get it now. So, it's only going to help you to convert the full wave rectifier, that is, okay, let me just show you what I'm trying to say so that you understand what I'm saying better. This is how your current flow for an AC current. AC current flow like this. That is alternate current. So when you use diode is going to help you to convert it to half wave. So this is not still okay. Are you getting it now? So to convert it to direct DC, you know, this is DC. DC current is just like this. Are you getting it now? So in order to convert this one to direct DC, then you need capacitor. So capacitor will complete the job of smoothing this particular job that the junction diode has done. The junction diode has helped you to what? Reduce the full wave rectifier, full wave AC currents to half wave AC current. The capacitor is going to do the complete smoothing. So if you really want to see a few details about this, then you can register for my class, a special physics class. Then you can talk about more under rectification of basic electronics in detail. So, but for now, this is just what you need to understand as far as JANB is concerned, or WAEC. Is that taken now? So it also serves as a regulator. It serves as a regulator or control in a circuit. And the third one is that it's used in detecting, protecting, and it serves as a switch. So do you get this now? So these are some of the uses of the junction diode, or let me just say semiconductor diodes. Because for this particular one, as a regulator or control in the circuit, we use Zener diode for this. Zener diode will help you to control the amount of current that should enter into a particular circuit. So when the current that wants to enter into that circuit is greater than the specification, what will happen is that it will cut. Because of the Zener diode is going to do what? It's going to cut the current. So instead of you to destroy the entire circuit, you only replace the Zener diode. Is that taken now? So that's what about that. Okay, so what are the advantage and disadvantage of junction diode and thermionic diode? So we have thermionic diode, or when you talk about thermistor and the likes. So advantage is that for junction diode, no ether. They are very cheap. They are much smaller in size and weight. So okay, when I give one pack of LED is about 1,000 pieces. It's very light when you are holding it. So junction diodes or semiconductor diodes, they are very cheap. One is 30 naira. It's very cheap. That's number one. Number two is that they don't consume more of it. Either they don't produce heat, let me put it, I don't generate heat. Are you getting this? And they are very, very light in weight. So you are not going to use them for anything electronics, and you expect the electronics to be as heavy as something else. No. So what is the disadvantage? They conduct slightly in the reverse direction. They conduct what? Slightly in the reverse direction, and they are temperature sensitive. That is, if the temperature is just too high, they can get what? They can get damage. Are you getting it now? So please, let me just quickly fix something here. I think pause. Okay, so I think we can continue now. Well, my issue now is I don't know if this thing is recording or not. Okay. All right. So let's continue from where we stopped now. So that's about can you guys hear me?
Yes, sir.
All right. So I hope you understand the aspect of semiconductors and junction diode better now, right?
Yes, sir.
All right. So let's move on to the concept of what's happening. Sorry, my charger is not plugged. Okay. All right. So let's take some questions under this before we go to transistor, if we can do that today. So let's take some questions under the semiconductor of the thing. Okay. Okay. So let's take some questions then. Are you ready? Are you ready?
Yes. Yes, sir.
Okay. So we have question number one. Question number one. So the question states that the bond between silicon and germanium is A, covalent, B, trivalent, C, ionic, and D, dative. So you can get the right answer there.
Covalent.
Covalent.
Covalent. Covalent, correct. So because they are group 4 elements. Okay? So the second question states that intrinsic semiconductor atoms are bonded together by A, covalent bonding, B, ionic bonding, C, thermal fission, and D, secondary bonding, and E is metallic bonding. So what would be the right answer there? Intrinsic semiconductor atoms are bonded together by A, covalent bonding, B, ionic bonding, C, thermal fission, D, secondary bonding, E, metallic bonding.
Covalent bonding.
Covalent
Covalent bonding.
bonding. Okay, so that's correct. Okay, okay. So the question states that I think this is 2003, JANB 2003, question number 45. The question states that the major difference between a pure semiconductor and a pure metal is that, listen to the question, the major difference between a pure semiconductor and a pure metal is that A, the resistance of metals increases the of metal resistance of metal increases with temperature, while for semiconductor it is the reverse. B, metals are harder than semiconductors. Metals are harder than semiconductor. Okay. C, metal have a forgiving gap. Metal have forgiving gaps, while semiconductors have not. And D, while the resistance of metals decreases with temperature, the reverse is the case for semiconductors. So which will be the right answer? The question says the major differences between a pure semiconductor and a pure metal is that. So what will be the right answer?
Towards D.
D states that while the resistance of metals decreases with temperature, the reverse is the case for semiconductor. So the question again is that the major difference between a pure semiconductor and a pure metal is that. So what will be the right answer?
A.
A.
That is, the resistance of metal increases with temperature, while for semiconductor it is reverse. So that's the correct answer. Thank you. Okay, so the next question here states that which of the following is a pure semiconductor? Which of the following is a pure semiconductor? A, silicon. B, carbon. C, transistor. D, phosphorus. So what will be the right answer there?
Silicon.
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 So, okay.
A.
So
Silicon.
silicon, that's correct. If I may ask, why can't carbon be the answer? Because carbon is also in group 4. And we said group 4 elements are semiconductor. Why is carbon not the answer? Why silicon?
Carbon has two allotropes. and one can conduct electricity. So it's
Thank
a
you.
semiconductor.
Thank you so much for that. So do you get that now? So when you say a pure semiconductor, they are insulator or pure conductor. Now they are insulator or they are pure conductor. Are you getting this now? But when you look at carbon, e.g. graphite, are you getting it now? Is a what? A form of carbon, and it is a good what? Is a good conductor. So that is why carbon can be the answer. So the correct answer is going to be either silicon or germanium. Thank you for that response. I so much appreciate. All right. So let's see another one. Okay. We have 2004. Please, I'm just going to read the question, and I want you to just pay attention to it. I'll read the question and the option. So please, just give response. 2004, question number 50. The question states that for semiconductors to have negative temperature coefficient of resistance implies that, think I omit the explanation of negative and positive temperature coefficient, but I'd like you to use your idea to carry it, and then you can see that the essence of solving questions. If we are not solving questions now, maybe we won't have time to explain that, but let's try if we can answer it genuinely. Davis, for semiconductors to have negative temperature coefficient of resistance implies that A, their resistance increases with temperature, B, their resistance decreases with temperature, C, they have electrons and holes at high temperature, D, their resistance is constantly changing with temperature. What is the right answer?
It's
Am I to take the question again?
yes, sir.
Okay.
Okay, the options.
For semiconductors to have negative temperature coefficient of resistance implies that A, their resistance increases with temperature, B, their resistance increases with temperature. That is A, their resistance increases with temperature, B, their resistance decreases with temperature, C, they have electrons and holes at high temperature, D, their resistance is constantly changing with temperature.
C.
They have electrons and holes at high temperature.
So it decreases with temperature.
Their resistance decreases with temperature. Okay, somebody say C, somebody say B. Okay, class, we are going to mark ourselves now. When something has a positive temperature coefficient of resistance, positive temperature coefficient resistance means it is directly proportional. If the resistance increase, the temperature will also have what? Must have increased. But when something has negative temperature coefficient of resistance, it means it is inversely proportional. When the temperature increase, the resistance will reduce. So what will be the right answer there? I'm asking who is correct among both of them. Are we still together?
C.
So the correct answer is going to be B. So when they say something has a negative temperature coefficient, what it means is that the higher the temperature, the lower that thing. Is that it now? Okay, so let's go to the next question. And the next question tells Roman figure 1, small size. Roman figure 2, low power requirements. power requirements. Roman figure 3, not easily damaged by high temperature. Roman figure 4, highly durable. So the question says, which of the above are the advantages of semiconductors? Which of the above are the advantages of semiconductors? A. Roman figure 1, Roman figure 2, and Roman figure 3 only. B. Roman figure 2, Roman figure 3, and Roman figure 4 only. C. Roman figure 1, Roman figure 2, and Roman figure 4 only. D. Roman figure 1, Roman figure 2, Roman figure 3, and Roman figure 4. So the question states that which of the above are the advantages of semiconductors? You saw what?
B.
A.
A. Roman figure 1, 2, 3 only. Okay?
Yeah.
So are you saying that they are not doable?
B. Sir, option B.
Eh?
Option B.
Option B, 2, 3, and 4. Are you saying they are not small? Do you take anything down in the class? The correct answer there is going to be D, to save our time. So semiconductors are small in size, they require low power, and they are safer to work with. Are you getting it now? So semiconductors are not easily damaged and they are highly durable. So the correct answer is going to be D. Which of the following statements are true about semiconductors? Which of the following statements are true about semiconductor? We want to go 1. Doped semiconductors are extrinsic. Are extrinsic semiconductors. So, Roman figure 2, germanium can be used. Germanium can be used as an intrinsic semiconductor. Roman figure 3, silicon can be used as an extrinsic semiconductor. Roman figure 4, materials used for doping. Material used for doping semiconductor have 4 valency electron. Have 4 valency electrons. Option A, we have human figure 1 and 2 only. Option B, human figure 2 and 4 only. Option C, human figure 1, 2 and 3 only. Option D, human figure 1, 2 and 4 only. Option E, human figure 2, 3 and 4. So which one is the right answer there? So the question states that which of the following statements are true about semiconductors? Human figure 1, doped semiconductors are extrinsic semiconductor. Somebody say something?
A.
Okay. Do you all agree with her?
A.
Yes, sir.
So the correct answer there is A. That is, doped semiconductors are extrinsic semiconductor. Germanium can be used as intrinsic semiconductor, but silicon is an intrinsic semiconductor, not extrinsic. Then the material used for doping can only have either 3 valency electron or 5 valency electron. Okay. So let's move to the next question. Doping in semiconductor is doping in semiconductor is a process of purifying the semiconductor, material. B, correct connection of semiconductor devices. C, addition of small amount of impurity, impurity to the semiconductor, the semiconductor crystal. D, process of forming a PN junction. So what's the right answer to the question now? The question says doping in semiconductors is
Option C.
addition of small amount of impurity to the semiconductor crystal. So that's correct. Okay. Okay. 2005 question number 4. 2005 question number 4 states that when impurities are added to semiconductors, the conductivity of the semiconductor A increases, B decreases, C remain constant, D increases then decreases.
Increases.
It increases.
Increases.
Correct. Materials used for doping semiconductors have valencies of A3 and 4, B5 and 6, C4 and 5, D4 and 6, E3 and 5.
5.
3 and 5.
3 and 5. So the correct answer is E. 1999 question 43. 1999 question 43. In semiconductors,
5.
1999 question 43. In semiconductors, the carriers of current at room temperature are A. Electrons only, B. Electrons and holes, C. Holes only, D. Electrons and ions.
Electron and holes.
Electrons and holes. In semiconductor, positive charges are also called A. Electrons, B. Holes, C. Neutron, D. Ions.
Holes.
Electron.
Electron.
In semiconductors, huh?
Holes. Holes.
Holes.
So the correct answer is holes. The positive charge carriers are holes, while the negative charge carriers are electrons. Okay? If a donor impurity, listen carefully, if a donor impurity is introduced into a silicon lattice, if a donor impurity, this might be kind of tricky. If a donor impurity is introduced, the donor impurity is introduced into a silicon lattice, the resulting material is A. N-type silicon, B. P-type silicon, C. richer in electrons, O's pairs, D. richer in O's only. So what will the right answer to the question now? If a donor impurity is introduced into a silicon lattice, the resulting material is
Option C.
option C, richer in electrons, O's and pairs. Is that what he said?
B.
B, P-type silicon. Okay. Any other answer aside from that? Okay. If that is our option, the first question is you ask yourself is that what are donor atom and what are the acceptor atom? So when we talk about donor atom, we are talking about the group 5 atoms. They donate to them. Are you getting it now? And when we talk about acceptor atom, they are group 3 elements. Group 3 are acceptor, while group 5 they are donor. So when you add a donor atom to silicon, that means you are adding impurity pentavalent to silicon. And when you add pentavalent atom to silicon, you are going to add what? N-type silicon, that is N-type semiconductor. So if it is what? Acceptor atom is going to be what? The trivalent atom, which is what? P-type. Do you understand that now?
Yes, sir.
Okay. Okay. The next question states that an N-type semiconductor is formed when a silicon material is doped with an element of group A2, B3, C4, D5, E6.
3.
So the question says that an N-type semiconductor n-type semiconductor is formed when a silicon material is doped with an element of group A 2, B 3, that is A group 2, B group 3, C group 4, D group 5, and E group 6.
Group 5.
Group
Group
5.
5.
Group 5. So the correct answer is D. 2006 number 5. 2006 number 5. The question states that a certain manufacturer wishes to make a n-type semiconductor. A certain manufacturer wishes to make a n-type semiconductor. Which materials would he select for doping? Which materials would he select for doping? A. Arsenic and antimony. B. Aluminium and indium. C. Boron and antimony. D. Helium and boron.
Please repeat the question.
A certain manufacturer wishes to make a n-type semiconductor. Which materials would he select for doping? A. Arsenic, and antimony. B. Aluminium and indium. C. Boron and antimony. D.
Boron and antimony.
Helium and boron. So what is the right answer?
D. D.
Option A.
Option A, arsenic and antimony, because the person needs group 5 elements. Okay? Silicon doped with aluminium and germanium. Silicon doped with aluminium and germanium, doped with arsenic become. Okay, so let me put the question down. It might be confusing. So the question states that silicon doped with aluminium and germanium doped with arsenic become. Silicon doped with aluminium and germanium doped with arsenic become A. N-type semiconductor. B. P-type semiconductor. C. N and P-type semiconductor. D. P and N-type semiconductor. So what will be the right answer?
P and N type semiconductor.
P and N-type semiconductor. So that's correct. Okay, let's look at these last two questions before we call it a day. Okay, so the question here states that in a semiconductor, junction diode, hold on please. Okay, in a semiconductor, junction diode has the depletion in a semiconductor junction diode, comma, as the depletion or barrier layer is forward biased, the layer A narrow, B remains constant, C widens, then narrow, then D widens. So which will be the right answer there? In a semiconductor, junction diode, as the depletion or barrier layer is forward biased, the layer A narrow, B remain constant, C widens, then narrow, D widens.
Sabi.
It remains constant, so the correct answer is going to be A. It's narrow because the current will flow and resistance will reduce. So once resistance reduce, it means that depletion layer, which we call the resistance layer, is getting shrinking. Are you getting it now? So the correct answer is A. Okay, and I think okay, let me say the last one, the last question, 2006 number 10. 2006 number 10. The question says that the battery connection that permits current to flow across a PN junction is called the battery connection that permits current to flow across a PN junction is called the battery connection that permits current to flow across a PN junction is called A. Amplification, B. Rectification, C. Forward bias, D. Reverse biased.
So
So forward biased. So I think it will be nice for us to stop here today. So by God's grace, in our next class, we are going to continue. In our next special class, we're going to continue by looking at transistor. And once we are able to finish with transistor, we move down to another topic that are also special topics like this. So all these silence topics and difficult topics, so we are going to be bringing them up under the special physics classes like this. Okay, so this will be our first special physics class. So I'm going to upload this for public to have a view of it so that we can have more people to sign up for this program, and I think with that we are going to help a lot of people to pass this. So by 2 o'clock, sorry, by 4 o'clock, you are going to be having a biology. So for biology students, don't forget to join the class by 4 o'clock. So I think math students will be free today since they are occupied yesterday. So any questions so far before we call it a day? Is there any question? All right. Alright, so in the absence of no question, thank you for making it to today's class. I so much appreciate every individual that makes it to today's class. So thank you. See you guys in the next class. By His grace.